So before understand what is diode and its circuit application, okay, let us understand what is PN junction. So let me give briefly the introduction of semiconductors. Okay, so semiconductors are the materials which has conductivity of these materials lies between metal and insulators. Now there are two type of semiconductors. One
Sir,
is
your voice is breaking.
थोड़ी आवाज खराब आ रही है.
Is it okay now? Am I audible
No,
now?
sir.
No.
No, sir. No, sir.
Can you hear me now?
Yes,
Yeah.
sir.
Sir, clear.
Okay. So the conductivity of semiconductors lies between metal and insulator. Okay. So basically there are two type of semiconductors. Okay. One is called intrinsic semiconductor. Okay. Also known as the pure semiconductors. But the conductivity of these intrinsic semiconductor is very low. So they don't have a much practical applications. Okay. So in order to increase the conductivity of intrinsic semiconductor, we dope some impurities in these intrinsic semiconductor, okay, and we make them extrinsic. Okay. So the next classification is extrinsic semiconductor. Now extrinsic semiconductor again can be classified as, so these are basically doped or impure doped semiconductors. Okay, and this is also can be called classified as N-type and P-type semiconductors. Now let us understand what is intrinsic semiconductor. Okay, why it has a very low conductivity. Okay, so low conductivity, these material have a low conductivity. So because of low conductivity, they are not useful. Okay, so in order to make them useful for practical applications or making devices, we increase the conductivity by mean of doping. So first we'll understand why these material have a low conductivity. Then after that we'll discuss how can we increase the conductivity. Okay, so put the heading now, intrinsic semiconductors. Okay, so if we see intrinsic semiconductor, let me take example of silicon. Okay, so silicon is a fourth group element. Okay, that means it has a 4 valence electron, and it is, every silicon atom is bonded with a surrounding another other silicon atoms. So this is the crystal structure of silicon. This is the crystal structure of silicon. So it is a 4 electron and these 4 electron it is sharing by with neighborhood silicon atoms. Okay, so here say we have one more silicon atom. Here we have one more silicon atom. Okay. Say here we have one more silicon atom. So you can understand each silicon atom is surrounded by 4 other silicon atoms. Okay, let me make one more here also. And these silicon atoms have a covalent bonding, connected with a covalent bonding. Okay, so this is the ideal crystal of or silicon. Okay, and they have covalent doping, covalent bond. Now if you see this crystal structure, okay, you find all the electrons are used in the making the bonds. Okay, so no free electron is available. If there's no free electron available, obviously this material should show either zero conductivity or low conductivity. So if I say at T is equal to 0 Kelvin, T is equal to 0 Kelvin, this is the situation. Okay, all the electrons are perfectly bonded with silicon atom. So if I draw the energy diagram of this one, so basically this is the energy diagram of semiconductor. This is your valence band and this is conduction band. Okay, and somewhere here is the Fermi level at the middle of the gap in intrinsic semiconductor, and at T is equal to 0 Kelvin, okay, valence band is completely filled. Valence band is completely filled. Okay, at T is equal to 0 Kelvin. That means if I assume that this is the pure crystal, pure and ideal crystal. Okay, so it is a pure crystal, there is no impurity, there is no defect. So at T is equal to 0 Kelvin, all the electrons, these electrons are in valence band and conduction band is empty. Conduction band is empty. Okay, at T is equal to 0 Kelvin. So at 0 Kelvin, your semiconductor in pure states behave exactly like an insulator because it has no electrons. So if there's no electron in the conduction band, it will not conduct electricity. Okay, it's behave like an insulator. Now situation changes if you slightly increase the temperature. Okay, say in room temperature. Okay, which is room temperature is 300 Kelvin. Okay, or you slightly increase the temperature, or you go beyond 20 Kelvin. Slowly what happens? Okay, because of this thermal energy, okay, there is a thermal energy, and there is as well as you have a surrounding energy. Surrounding energy, you can't keep your semiconductor in the dark. Okay, so it is placed somewhere, light is falling, that is the energy. Okay, then there is some heat energy, and there is a always quantum mechanical probability. Now this electron do not have a sufficient, even though this electron do not have a sufficient energy to reach here. Okay, because there is a barrier, but quantum mechanically we know there is always some probability. Okay, even though my electron, okay, is here and it want to come here, it do not have energy, the energy is somewhere here and it has to cross this barrier. Okay, so quantum mechanically it is possible through tunneling or some mean. Okay, this electron, some of this electron can reach here. Okay, but these, the number of electron which is reaching here, they are the function of temperature. Okay, if temperature is low, there is a probability that these electron can reach here, but then also the probability is very low, that is minus exponential. Okay, so some of very low probability, some of electron can come here. So similarly here also even though this electron do not have some sufficient energy to reach this one, okay, they may come here. Okay, you can understand in a way. Okay, we can only talk sense, because they are giving some conductivity. So from where the electrons are coming, either the electrons are coming somewhere here, some defects are there, defects, because defects will modify the levels of the silicon, or there is some impurity atoms are present here, who is giving electron here. Okay, so there's some electrons are reaching here, somehow some mean they are reaching here, so that mean we have to just philosophically tell, okay, that somehow they are reaching, okay, because quantum mechanical probability you say, or you say this band gap is around 1 electron volt, okay, around 1 electron volt. So 1.1 is silicon, so silicon it is a 1.1 electron volt. For silicon it is a 1.1 electron volt band gap. Okay, this is a band gap, Eg. So now light, if you say the light energy itself is a 2 to 3 electron volt. Okay, that should be sufficient to make this electron go from this part, this to this here. Okay, and thermal energy is very low. Okay, thermal energy is kT. So if I talk about 300 Kelvin, the thermal energy is only 25 electron volt. 25 milli electron volt, and 25 milli electron cannot make this electron to go to here. Okay, conceptually. Okay, but there is even though energy is very low, some finite probability is there that when you increase the temperature, okay, some of the bond can break. Okay, so if you increase the temperature, increasing temperature, okay, if you increase the temperature, okay, some electron, okay, some electron, if few electron can jump to conduction band, if few electron may jump to conduction band, and because the energy gap is very high, so only if you can come. Okay, so that is the conductivity is very low of this type of semiconductor. Okay, so there is a no practical use now because there semiconductor has many other properties, like hey, this is a high mobility. Your conductivity can be controlled. Okay, you can manipulate, control in devices. Okay, so that they are very useful for making devices, but we have to we want decent type of conductivity. Okay, so this we cannot work with this low conductivity of internal semiconductor. Okay, so what we do, we make extrinsic semiconductor. Okay, the next heading is extrinsic semiconductor. Now extrinsic semiconductor is what? Again, two type. If you replace, say, first n-type semiconductor, n-type. So for n-type, you have to dope fifth group element in to replace the silicon with the fifth group element, okay, which has a one extra electron compared to the silicon atom. What are the fifth group element? Tell me, which are the fifth group element? Arsenic, okay, arsenic, antimony,
Bismuth.
bismuth, okay. These all are fifth group element. Fifth group element means they have 5 valence electron. Now suppose if I replace one arsenic atom with this silicon atom, okay, so you have to replace some atom. Okay, replace means you can't replace all the atoms or 10% atoms, because if you replace too many atoms, what will happen? The crystal structure will not be unique. Are you getting? The material itself will change. If you can change 50% of atom, then this is not silicon, that becomes something
Yes.
else. Okay, so you can dope only very low amount. Okay, say 0.1 molar percent. Okay, or maximum 1% if you want. 1% is very too high. 0.1%, 0.01%, very low you have to replace. Okay, and 0.1% is also very high. 0.1% means how much? If you take 1 mole has a 6 into 10 raised to power 23 atoms. Okay, if you even do 0.1%, that will be around 10 raised to power 20 atoms. 6 into 10 raised to power 20 atoms. That is also very high number of atoms. Okay, so that amount of atom you have to replace here, and once you replace here, what happens? This arsenic atom has a extra electron which is bonded. Okay, so you can assume this is like a neutral core and with a nucleus, and one electron is free. Okay, like a hydrogen atom. That's why we say impurity atoms behave like a hydrogen-like atom in the semiconductor. Okay, so whenever you do calculation, you will study when you do semiconductor. Okay, in your material also semiconductor chapter is there. That is very written by me only. That is very self-explanatory. So there you can go in deep, you can understand the semiconductor, and it will be discussed again in the solid state physics part also. So now, if you take this arsenic, it has a one electron which is loosely bounded. If you give some temperature, what happen? External semiconductor. Now, if you draw the energy level of extrinsic semiconductor, what will happen? The energy level of arsenic, okay, that means it is very close because it's a valence electron. I'm drawing the first excited state of this arsenic. If I want to ionize arsenic, okay, well, because this is a neutral atom, na? If silicon is neutral and you are adding arsenic, which is also neutral, so if I want to remove this one, that means the outermost electron of arsenic, okay, then this will become arsenic plus. Okay, this atom will become arsenic plus. So basically, and the energy which require to make free. When I say atom required energy to make free, okay, free means I have to send this electron to the conduction band. If I want to send this electron, this is covalently bonded. I have to send this electron. I have to come the valence band, and from valence band to it will come here. But this is not a valence electron. These are valence electrons. This is not a valence electron. Okay, this is a very loosely bounded with the arsenic, and if you supply some energy, this will come to the here. That means this level should be somewhere here. Okay, now reaching from here to here, it is difficult, but reaching from here, taking electron from the arsenic is very easy. So this is your arsenic. Okay, so what arsenic can provide electron to here, one electron to here. Okay, if four atoms are ionized, so if we assume at room temperature, whatever atoms we are giving, that will be all get ionized completely. If it is the case of complete ionization, okay. But in practical, if you are four atoms, if your ionization is 90%, 80%, so if there are 100 atoms, 80 atom are ionized, so you get 80 electrons here. So for example, here I am putting four atoms are ionized, so they become plus. They are donor atoms. Okay, they are donor atoms, so they will get positively charged. Okay, and now what about a Fermi level? Fermi level is always the topmost level. Okay, topmost level. There at t equal to 0, there cannot be any electron below this Fermi level. Okay, topmost filled level. Okay, so here intrinsic, it is in the middle. Intrinsic level is the middle, but Fermi level of n-type material, which I demonstrate by or represent by EFN, this is in between this donor level and conduction band. Okay, so this is called EC and this is called EV. This is the bottom of top of valence band. Is a conduction. This is the bottom of the conduction band. In between these two gap, this Fermi level present. Fermi is a hypothetical level. It's not exactly some kind of level. Okay, just so the mathematical understanding. There's a level. Okay, there should be some level. Okay, from which at t is equal to 0. T is equal to 0 means what? T is equal to 0. These you cannot ionize these atoms. So all electrons are here, all electrons are here, all electrons are here, all electrons are here. But give some temperature, then electron can go here. So somewhere your Fermi level should be in between, at t is equal to 0, it should be between these two levels. And if temperature varies, of course, the position of Fermi level will also vary. Okay, so that we won't go that deep. We don't require for diode to go in depth analysis. So what is the point here? Now this electron can reach here. Now if you are giving some temperature, so there is a finite probability these electron also can come here. Okay, so but here the majority charge carriers, these are the charge carriers, whichever carriers will conduct the electricity, that is called majority charge carriers. So in n-type semiconductor, these are the majority charge carriers. Majority charge carriers, okay, are electrons. Okay, of course, some of the electron can come also here, so you will have holes, and holes also, these are the semiconductor, these are minority charge carriers. Minority, they can also flow, produce current. Okay, so these are minority charge carriers. These are minority charge carriers, and these called holes. Okay, so in the case of intrinsic, you can get the electron, this electron from only from here. So the number of electron is equal to number of holes. This is the intrinsic case. Okay. But here is not the case. In n-type, you have number of conduction electron is more than number of holes here, because these are the majority charge here. This is the n-type semiconductor. Okay. So here your atom is donor. Okay. So pictorially, if I want to represent a n-type semiconductor, how should I represent? Okay. So pictorial representation of n-type semiconductor. Okay. So put that in pictorial representation of n-type semiconductor. Okay. So basically, if you have this one, okay. So this is your conduction band. This is your valence band. Okay. And here I have a energy level of donor. Okay. And here somewhere I have a Fermi level. Okay, so that we have already seen. Okay, now pictorial representation means different. Pictorial representation means how to represent a n-type semiconductor. So for example, this is, we have cross section. Okay, now I want to call this n-type semiconductor. So what I will do, either I will put here impurity atoms which are donor, positively charged, which is positively charged. So always these are ions. Okay, fixed ions in the lattice. Okay, of course there are so many silicon atoms also, but I want to represent this material is n-type. So n-type I will represent by type of impurity, and here the type of impurity is donor, and each donor has a one electron, because this is neutral as a whole. The section of this material is neutral, so each positively charged ion has one electron also present. Okay, which is loosely bonded with this one. Okay, so this is pictorial representation of n-type material. Okay, this is n-type semiconductor. Either you represent n-type material like this, or there is a possibility you can also represent n-type material. Generally this is the way you represent, or you can also represent, because the electrons are the majority charge carriers, you can say here these are the majority charge carriers. Okay, so this is also a kind of representation of n-type semiconductor. Okay, but generally we require this type of, because this gives much more information. Okay, while understanding, so we'll represent n-type semiconductor like this. So this is one part section, because we have to understand how p-n junction behaves. So I should able to represent what is n and what is the p when I'm forming a p-n junction. Okay, now next thing is your p-type semiconductor. Okay, so let us talk about the p-type semiconductor. So what is a p-type of semiconductor? Let us draw, put the heading p-type of semiconductor. So p-type of semiconductor. So p-type means, now the
Trivalent impurities.
okay, doping will be trivalent atoms. That is aluminum, boron, and
Phosphorus.
phosphorus is fifth group element. Okay,
Gallium.
gallium you can put,
Indium.
aluminum, iridium. Okay, so these are the trivalent impurities. So now you have a silicon, here. silicon. Okay. Now what you'll do, you will replace this by say aluminum. Now aluminum is trivalent impurity. Okay, trivalent atom or impurity. So it has only three electrons. Okay. So now this it cannot share here. So here is the vacancy, because this can only share 3 electron with the neighboring electrons. So it has only one hole is present in the lattice. Okay, wherever the atom is there, one vacancy is there. Okay, a vacancy is called hole. So now if I represent, you can draw some atoms here also. Okay, you can make a crystal. Okay, so this is the ideal p-type crystal. Ideal p-type crystal. So without other defects, other type of defects also there. Okay, but just so this is your EC, this is your EV. Okay, now what will happen here? Here you have the energy level. Okay, because now this is the acceptor, it can accept one electron. Okay, now suppose one electron moves from here to here. Okay, so this aluminum will become negatively charged, because it can accept, it has a vacancy. Okay, so this is the energy level of acceptor, which is very close to the top of the valence band. And say this is aluminum sitting here, aluminum atoms are sitting very close to here. Okay, now because they have one hole here, so now electron can go here. Okay, even at a low temperature, room temperature, there is a very good probability. Okay, reasonably good probability or final probability that these electron can be captured by these holes. Okay, so that means this electron can come here, wherever the aluminums are present. Okay, so if all the ionized, so once they take electron, they become negatively charged. And when this electron here, you have holes in the valence band, and holes in the valence band also are the charge carriers. Okay, so now, and some electron can go from here to here. That is also possible. And you get some more hole here. Okay, so now you have these electrons are the minority charge carriers. Minority, because their number is low, so we call it a minority charge carriers. And these electrons are called majority charge carriers. Holes, majority charge carriers. So holes are majority charge carriers, electrons are minority charge carriers in your p-type semiconductor. Okay, and the Fermi level is again, okay, somewhere here is the Fermi level FP, position of Fermi level. Now Fermi level is very important concept. Okay, while while you making two material joined together. Okay, so for conduction mechanism, understand the conduction mechanism, and the concept of Fermi level is very important. Now again, the pictorial representation, how I will represent p-type material. Okay, so representation, okay, pictorial representation of p-type material. Of p-type material. Okay, so again, take a section of the material, and impurity atoms are now negatively charged. Each impurity atom okay, and you can place one hole here. You can present a hole here. Okay, so this is the pictorial representation of p-type material. Okay, where impurity atoms are acceptor. These are acceptor ions, and these are the charge carriers. Majority charge carriers. Okay, these are the majority charge carriers which are present in the valence band of this material. So this way you represent a p-type material. Okay, now let us understand what happens when you make a p-n junction. That means when you are bring a n-type and p-type material and you're joining. Okay, so now put the adding PN junction. Okay, so let us discuss the PN junction. Shall I erase this one?
Yes, sir.
Okay. Now, PN junction means you have a junction between PN and material. Okay. So basically, you have a P-type material now. Okay, and you have an N-type material now. So I'm placing the isolated material. Okay, this is the isolated material. Isolated material. Okay, so this is a P-type. That means you have here electrons. This is my P-type material. Okay, and here you have donor atoms. Okay, so here you have holes. You have holes here, holes here, holes here, holes here, holes, holes, holes. Okay, holes, holes, holes. Okay. Here you have electron, 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 electron. This is my P-type, and this is my N-type. Okay. If I see the energy diagram,
सर उल्टा होगा ना?
क्यों? N-type में तो एटम डोनर होता है ना,
मेजॉरिटी चार्ज कैरियर.
तो इलेक्ट्रॉन है ना यहाँ पे.
ओके
ओके, these are electrons. ये होल्स, ये समझाने के लिए तो मैंने वहाँ पे वो अलग से ड्रॉ किया था पिक्टोरियल रिप्रेजेंटेशन. पिक्टोरियल रिप्रेजेंटेशन ऑलवेज material will be represented by the sign of its impurity. Okay. Now what happens? This is isolated bar, isolated p-type material, isolated n-type material. Okay. If you see their energy diagram, it is my EC. Okay. And this is my EB, top of the valence band. Okay. And somewhere here is the Fermi level. Okay. Now impurity atoms, I'm not drawing. If you want, you can draw impurity atom also, but that is not required to understand the conduction mechanism. So just I'm putting here the Fermi level EFP of p-type material is present here. Okay. And here say this is my n-type material. So this is my, now material is same. It is a silicon, you are doping something, silicon, you're doping something. Okay. So the energy band diagram will not affect much with impurities. Okay. Because impurity, you're putting a very less impurity. Okay. Remaining of the section of the material is same. So why should the band gap should change? Okay. Band gap is almost same. So the gap is always same. Only the position of Fermi level is shifting. So this is EC and this is your EV. And here you have Fermi level, we call it EFN. Okay. EFP and EFN. Fermi level n-type material. Why intrinsic is present here? Intrinsic here is, it is intrinsic Fermi level. Okay. That we don't require here. So this is the condition in the beginning when they are isolated apart. Now, when you join together, so when I say in order to make a PN junction, we are taking a n-type and p-type joining. Actually, that doesn't happen like this in the practical situation. Whenever you are making a device, okay, there are some methods by which you form the junction. Okay. So ideally, what people do, people take a, say, a ideal silicon crystal, they dope inside the silicon n-type impurity. So this become n-type material. Now, half of the, say, partial section of this part, okay, they dope a high amount of p-type impurities. So in this way, a PN junction is formed by diffusion process. Okay, you don't take a separate n-type, p-type and join together. That way you cannot join. Okay, because these two are separate material. they are separate Fermi levels, and when you are want to combine together, okay, so once they combine together, they should become one material, okay, one section, whichever one section should be there. So one section only can happen when their Fermi level should align. Are you getting my point? Okay, that is a one material can have only one Fermi level. So when I am bringing a p type and n type material, okay, so even though so say I have a this section of, say, what I say this is my a crystal, okay, so this crystal, what will happen, this part, half of the part is, say, n-type material, okay, so half of the part is n-type material, and say no, say bottom material is, bottom half is n-type material, and top half is my p-type material. But in between these two materials there is a junction, okay, this is the p-type, this is the n-type, okay, joined together. But there, when they are getting joined together, okay, there is some part which will behave differently compared to the right and left side of sections, okay, that part is called a junction. So there is junction mechanism is different, okay, junction characteristics are different than this side or this side of anti-material. So what happen when you are making junction, that means your Fermi levels are aligning. So here now I am only going to draw the energy band diagram of only what, only of junction, not the whole material, okay. We want only junction. Here is the semiconductor, here is the semiconductor, between there is junction, and what is happening in the junction, that is the important thing for us. So now, here you have you have electrons. So electrons, I'm putting a say this part dark, the circles. So here n type I have electrons, okay, large number of electrons, and here p type material, okay, I have holes. These are holes, and these are electrons. These are electrons, majority charge carriers, okay, electrons which are majority charge carrier, majority charge carriers. Of course, yes, here also some electron also there, some electron can go from here to here. So here also some electrons are there, but they are minority charge carriers, they are minority they are minority electrons, okay. Similarly, here some holes are there, okay, they are minority holes, okay. Now what happens when you trying to join them together? So there is a concentration gradient, okay, here this side, okay, higher concentration of electron, this side is higher concentration of holes, okay. So whenever there is a concentration gradient, what will happen? Diffusion will take place. So diffusion of electrons, okay, these electrons, okay, so these electron will diffuse, similarly you can say these hole will diffuse towards the junction, diffuse, okay. And diffusion, when the diffusion is take place, these electron will go and combine, with these holes, these electron will combine. We'll see how it happens. So now these electron, because they have high energy, these are the energy levels of electron, not holes. I'm drawing the energy levels of electrons, okay. So electron always can move from very easily without any electric field or without any force. If it is higher energy level, it can move to the lower energy level very easily, okay. But holes also can move from holes, it's the opposite thing. Holes also can go from here to here, okay. The thing is, only one is moving, these are not moving, okay, because actually these are moving, but because when these combine with this one, here one hole is consumed, so we say holes also moving, okay. In reality, holes cannot move, no. Only electron can jump from one hole to other hole, so it's appears like that. You can represent that holes also moving, okay. When electron come here, you say holes is moving. Okay, so that is thing. So electron always can go from higher level to lower level, and holes can always jump from lower level to higher level, because the hole's energy decreases when it move in the, when it move go up. Hole's energy decreases. Okay, in this energy level, you have to understand this way. Whenever holes want to go down, they cannot go. Whenever electron want to go up, they cannot go without a push. Automatically, this transport is not possible. Okay, so now what will happen? Because there is a high concentration of electron, high concentration, so obviously diffusion will take place. These electron will recombine with one. Okay, so when electrons are recombining with these holes, okay, so you say diffusion take place. Okay, so electron get recombines with holes. Okay, so when electron get recombined with the holes, what happen? The concentration of electron decreases here, and concentration of holes decreases here. Okay, and but this diffusion cannot take place infinitely time, na? The electron cannot keep on moving. All the electrons are there. 1 million, 1 million or 1 billion electron. They all cannot go here. Somewhere this process will stop. Okay, we are talking about that process. So electrons are diffusing and then combining with these holes. Now here holes decreasing. Now intrinsic semiconductor, electron and holes are equal, and the Fermi level is in between. Whenever I drive the condition of Fermi level, I put a number of electron, number of holes are equal. That will give me the position of Fermi level, which is here. But here now when I'm removing these holes, again my Fermi level will shift towards intrinsic side. It will move up. Similarly, here when I'm removing electrons, again it is going towards a intrinsic nature. Intrinsic means this equal. This number is decreasing. So slowly, this will come down. Okay. So because and this diffusion will take place until they don't have one single Fermi level. So when at junction, this will keep on moving and this will keep on downing. They both will align, and at that place, this material, the diffusion process of diffusion will stop. Okay. So the reason for diffusion is also the change in the Fermi level position. Even if you want to say you have wire, you want to draw a current, you can't draw the current until you don't create the Fermi level difference at the ends. You just keep current will not flow automatically. When you apply some battery and when you apply battery here, so electron energy level here plus side will go down, and electron energy level of negative side will go up. When you supply negative to negative, it will go up. When you supply negative to positive, it will go down. So when you supply wire, you have supply positive battery here. Okay, that means you are making the Fermi level of this side down and Fermi level of this side up. That's why your electron move from negative to positive side of the terminal, and we say current is opposite, positive to negative. Okay, so whenever you want to a flow of current, you have to create the difference of Fermi levels. Okay, now what happens? This is the isolate condition. Now you are making diffuse them. Okay, so this diffusion is taking place. Now at equilibrium, what happens? Let us see what happens at equilibrium. So at equilibrium, what will happen? Okay, so this part of the here you have these are your impurity atom this side. Now once they have lose the electron, they become positively charged. Similarly here you have acceptor ions. Once they get the electron, they become completely negatively charged. Okay, only at the interface, remaining part is not affected. Okay, there all the electron cannot go here. Okay, so at the junction, because of diffusion, electron goes here, they combine with this one, the electron goes, they combine here, remaining part is same, remaining part remains the same. Okay, That is, here is the electron and the hole, here the ion, this is negative ion. So I'm not, so I'm writing it as a p-type material. So remaining part is p-type material, this is the n-type material. Okay, that is not affected. Only at the junction where you're making this kind of process take place. Okay, so I'm not drawing the energy level of P and N. I'm only drawing the junction. Okay, this is the middle of the junction. This is say xn, say this is xp, boundary of n-type xn, and this is a boundary of p-type, and this is x is equal to 0. X is equal to 0. Okay, so I told you that band gap cannot change, so band gap has to remain same. Okay, so this is my EC and this is my EV, my EV. Now because this Fermi level is coming down here, Fermi level is coming down here, and Fermi level is going up here, so at the interface we are saying there is a band bending. So now here they have a common Fermi level. This is my common Fermi level, EFP equal to EFN. Okay, but this band gap cannot change. This band gap is remain the same, EV. Okay, but there is a bending of the uh, bending of the levels. So this will be, so it was near to n type, so it remains near to n type. Okay, and here it was near to p type, it remains the near to p type. But there is a to order to this to happen, there is a band bending. So this is your EC of p-type material, EV of p-type material, is conduction band of n-type material, this is a valence band of n-type material. So now this is called band bending, bending of energy levels. Okay, bending of energy levels, or band bending energy levels. Okay, now here this is the n type of section. Here we were having electrons in majority. Here we are having electrons in majority, and here we are having holes in the majority. Okay, of course here also some minority electrons were there. Okay, and here what was there? Here also some minority holes were there. This is the majority. This is the majority. Okay, this is the minority. This is the minority. Okay. Now, when some electron leave there here, so there is a barrier arises. Okay. Barrier arises means what? So because this become positively charged and this become negatively charged. Okay.
सर
Yes.
सर इसको एक बार समझाओ, और ये मतलब ये ग्राफ ऐसे टिल्ट क्यों है?
तो भी तुम इसको भी, ये फर्मी लेवल था शिफ्ट, इसका तो इसका नीचे जा रहा था,
हाँ
इसका फर्मी लेवल ऊपर जा रहा था, पर ये फाइनली इनका एक सेम फर्मी लेवल होना चाहिए, पर ये गैप भी मेंटेन होना चाहिए। तो कैसे बनेगा वो ग्राफ? ओके, तो वो बिना बेंडिंग के पॉसिबल नहीं है, बता रहा हूँ अभी, ठीक है ना। तो ये बेंडिंग का मतलब क्या है? एनर्जी लेवल में बेंडिंग का मतलब क्या है? डी बाई डी एक्स क्या होता है बताओ? डी बाई डी एक्स क्या होता है? ये एनर्जी लेवल है। डी बाई डी एक्स क्या होता है? एनर्जी अपॉन एक्स क्या होता है? ये पता है आपको? ई इक्वल टू माइनस डी वी बाई डी एक्स।
यस सर।
ओके, और यहाँ अगर मैं इसको Q से मल्टीप्लाई कर दूं, Q से इसको, तो क्या हो जाएगा? ये Q, और ये क्या हो जाएगा? डी एनर्जी, इसको मैं एनर्जी लिख देता हूँ कैपिटल की ई से, इलेक्ट्रिक फील्ड एनर्जी है, डी बाई डी एक्स क्या हो जाएगा? ओके, तो देयर इज अ ग्रेडियंट ऑफ एनर्जी लेवल्स, ग्रेडियंट ऑफ एनर्जी लेवल्स, बिकॉज यहाँ पर क्या हो गया? try to understand here, when your electrons are moving, this becoming positively charged, then this become negatively charged. Okay, and because of this movement, now here is a net electric field. Okay, or ये electric field, what is doing? This electric field, this electron field is stopping the diffusion, because this is a plus. This will not allow electric field is this direction.
Yes sir, yes sir.
This will not allow this hole to come here. This hole cannot come down. Electron cannot go move up. Electron can come down, and electron can go move up. But now what is happening with diffusion? Okay, there is a field is creating which is not allowing to diffusion to take place. If this field is not there, then the diffusion will take place infinitely. Okay,
Mhm.
because of the presence of, because there's wherever there's a presence of electric field, there has to be some slope of energy levels. There should be gradient of energy levels. Okay, the
Mhm.
presence of electric field shows there's a gradient of energy levels here. Okay, now this electron, these cannot move, these cannot move. Okay, similarly these suppose, and this cannot come down, this cannot come down.
Yes, sir. Yes, sir. Clear,
Okay,
clear.
this cannot move up, okay, this cannot come down.
Mhm.
And but this electron, here is the plus electron, plus is pulling this electron, this can move here. But you say if this is still moving, then what would happen if this is moving? Okay, but these are minority charge carriers. Okay, the electron moving from here to here, and equilibrium, and some electron moving from here to here, they balance each other. That is diffusion. When the electric field is there, okay, now so when you make the joint, so there is an exponential flow of current. Okay, large amount of electron move here, but when there is a junction, this equilibrium is established, only if few electron can go here, because of there is a quantum mechanical probability electron can move to here. So this is the diffusion can happen, a little diffusion can happen. So diffusion, and this is called drift, because these electrons are pulled by this plus. So at equilibrium, drift component is equal to diffusion component. Okay, net flow is zero. Net flow of charge in equilibrium is zero, because now here one electric field is present, which is balancing diffusion. So no diffusion happening, no drift happening. Both are happening. It's very little amount, but they are balancing each other. So we say there is no current flow, and equilibrium there is a one Fermi level. Okay. Now what I want for diode here. So basically your diode is a PN junction, and now once your PN junction is formed, even though there is electrons are there, majority charge carriers, holes and majority charges present here, but still there is no current without any force. Okay, because there is a one potential barrier. This is called QVBI. Okay, there is a potential difference. A barrier arises. Because of this barrier, no current can flow in a PN junction without a external field. Okay, now if I want to flow the apply if I want to apply the voltage, I want to flow the current through the PN junction. Okay, I can do in two way. I can apply forward bias, and I can apply reverse bias. Okay, so let us understand what happens in forward bias and reverse bias. Okay, so put the heading now, forward bias. So PN junction is forward bias. PN junction in forward bias. Okay, so let us understand what happens. Now there is no current. Okay, no current. So there is no current because both part are balanced. Okay, now forward bias means what? You're applying plus here, you're applying minus here. Okay, now practically what is happening when I'm applying plus here and minus here? Okay, that means what I'm doing, whenever P plus plus are connected, the energy level of that side go up. Okay, and electron is committed. So basically what I'm trying, if I'm applying this plus here, so this go up, this go down. So this go up. What happens if you apply plus minus here? That means I'm applying a electric field here, external electric field. So this is the internal electric field. I say EIN already present because of separation of charges. Now I'm applying a external electric field here in this region. Okay, because of this positive battery. Now this external electric field is opposite to the internal electric field. Okay, so what will happen now when I apply this one? So in equilibrium, when I apply forward bias, what's happening? This is the condition. Now this barrier, because electric field is decreased, the gradient of electric field, the amount of more the electric field, more the gradient. Okay, so now because electric field is inside the junction is decreasing, that means now what is happening? This part is become almost, this barrier width is decreasing. Okay, that means we are applying the field against V, against the external electric field. So what will happen here? Now this gap will become Q VBI minus V. Earlier it was Q VBI or VI. You put built-in potential. This is called built-in potential. This, the width of this built potential go down. Okay. Now here the majority charge carriers are there. So when the build is decreasing, now these electron can move here. Again, diffusion can take place. Okay, this because these electrons have kinetic energy, temperature energy, everything energy, and as soon you keep on increasing this one, this level go up, and again this level will go up and up. Then you can, then again the diffusion will take place. Diffusion will start dominating. So when I'm applying forward bias, basically what you're reducing this electric field. That means your minority charge carriers are not, minority movement is now decreasing, but the diffusion part is increasing because now width is, you have change this one. Okay, so diffusion of current take place. Okay, and here you have holes. Okay, and hole can also go down. Holes also can go down. So diffusion take place. So diffusion current will flow. Diffusion current flows in the material in forward bias or flows in PN junction. Okay, so forward current is that diffusion current. That always remember, forward current is diffusion current. Okay, here you have a minority electrons, here you have a minority holes, minority electrons here you have minority holes. Okay, so now because this will go up, then this cannot go here. Slowly when you applying voltage, you will become equal and then become up. So this cannot go here, but this can go here. So diffusion can take place and the diffusion current will flow. Okay, so this is the PN junction in forward bias. Okay, now let us see what happens in the so whenever you want to flow the current, okay, you have to create the difference of Fermi level. So when I'm applying this one, okay, again I'm creating the difference of Fermi level. Because negative to negative, Fermi level go up, positive to positive, Fermi level go down. So this is EFP, that is EFN, and the gap of these two levels, EFP minus EFN, again is Q VBI minus V, because this is this much is the gap. Okay, this is the potential we are applying here. Okay, that is the thing. Okay, because without the shift of Fermi level, current cannot flow, because equilibrium there is a one Fermi level. That means there become one material, and one material automatically current cannot flow. So you have to create the difference of Fermi levels. Okay.
सर
हाँ.
सर डिफ्यूजन करंट के लिए बेसिकली डिफ्यूजन एक ऐसा प्रोसेस है जो कि स्टैटिस्टिकल प्रोसेस है और जिसके लिए कोई भी इलेक्ट्रिक फील्ड की नीड नहीं होती है ना, ये एक
हाँ.
फिनोमिना है
हाँ.
जो डेंसिटी डिफरेंस से
हाँ. हाँ.
करंट फ्लो होता है। तो
हाँ.
यहाँ पे फॉरवर्ड करंट ये दिस इज कमिंग ड्यू टू इलेक्ट्रिक फील्ड,
No,
तो
इलेक्ट्रिक
हम
फील्ड,
डिफ्यूजन करंट क्यों कर रहे हैं?
इलेक्ट्रिक फील्ड के कारण नहीं आ रहा है। इलेक्ट्रिक फील्ड के कारण इलेक्ट्रिक फील्ड इसको पुश नहीं कर रहा है। इलेक्ट्रिक फील्ड क्या कर रहा है, इस बैरियर को हटा रहा है।
ओके,
बट जो वहां पे जो चार्ज फ्लो हो रहा है वो क्योंकि वहाँ कंसंट्रेशन ज्यादा है, बहुत ज्यादा है, कंसंट्रेशन बहुत ज्यादा है, इसलिए वो क्या कर रहा है, वो कर रहा है, वो कर रहा है। इलेक्ट्रिक फील्ड तो अभी भी है थोड़ा सा, तो ना ये प्लस है, ये इलेक्ट्रॉन है। इलेक्ट्रिक फील्ड तो क्या करेगा, इलेक्ट्रॉन को यहाँ पुल करेगा। इलेक्ट्रिक फील्ड तो ये है ना, इलेक्ट्रॉन को यहाँ पुल करेगा।
तो
सो
ये बैटरी का एक्सटर्नल इलेक्ट्रिक फील्ड है ना, जो हमने बैटरी
हाँ,
अप्लाई किया है।
तो एक्स्ट्रा हो जाएगा। तो यहाँ पे क्या हो जाएगा, यहाँ आपका प्लस हो जाएगा, या माइनस हो जाएगा। ओके, तो दैट वो भी पुल करेगा, बट वो करेगा यहाँ के माइनॉरिटी इलेक्ट्रॉन्स को। जो 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 फील्ड के कारण जो मूवमेंट होता है, ये जो जो वो हमेशा माइनॉरिटी कैरियर्स होते हैं। ये जो प्रोसेस हो रहा है, दैट इज अ डिफ्यूजन प्रोसेस। ओके, मैं जो यहाँ से पहले तो क्या हो रहा, डिफ्यूजन ही तो हो रहा था, और बैरल आ गया, डिफ्यूजन बंद हो गया, आपने फिर बैरल खोल दिया, डिफ्यूजन वापस हो गया। अंडरस्टैंड? क्योंकि ये करंट,
मैंने
बिकॉज ये करंट, दिस करंट इज वेरी हाई। अगर ड्रिफ्ट करंट लेने जाओगे तो ड्रिफ्ट करंट इतना ज्यादा नहीं मिलता जितना यहाँ की करंट मिल रहा है। ये एक्सपोनेंशियल करंट है।
यस सर,
drift current is not exponential current. Okay, so forward current is exponential current. Okay, so you note good point. Okay, forward current is exponential current. Forward current is high exponential current. Exponential current. और एक्सपोनेंशियल करंट आप 1-2 वोल्ट लगा के नहीं निकाल सकते, ठीक है ना? सो
ओके सर, ओके।
ठीक है, सो ये तो हो गया फॉरवर्ड बायस। नाउ व्हाट हैपेंस इन द रिवर्स बायस?
सर
हाँ,
सर आपने डायग्राम बनाया साइड में, उसमें वी बी आई माइनस वी, वो क्या होता है सर?
VBI माने V is applied voltage,
और वी बी आई सर?
VBI is built in potential, जो ऑलरेडी था ना, ये
ओके, बिल्ट इन पोटेंशियल।
built in potential, and this is the applied voltage. Okay, now what happens in the reverse bias? Reverse bias is different. Okay, now if you apply reverse bias here, okay, that is minus connected here, plus connected here, that means now external electric field also in the same direction. So in the first case you have to write, okay, the depletion layer bit decrease. In forward bias, depletion layer bit decreases. You wrote down there. Okay, so you have to make this little bit thinner. Okay, you can move one part. Okay, only one part, one section, you can show that is decreasing, okay, compared to the original. So what I'm saying now, in forward bias, okay, depletion layer but decreases, depletion layer width decreasing. Okay, so you can mention PN junction in forward bias like this one, plus minus, only one layer. Okay, now reverse, it become opposite. Okay, in reverse, what happens when you apply reverse bias, then field is increasing means this width is increasing, okay. Now this is width increases. Okay, width increases, so both internal field here and external field both are in same direction. Okay, so what will give, it will give like this, the barrier height will increase, barrier height will increase. Here you have a EFN, here you have, no, now what will happen, because you are applying minus here. Okay, so Fermi level will be here, EFP will be here, it will go up to the conduction band of this one. So this is EC and this is EVP. Okay, this is so EVN, and this is your ECP, and this is EVP. Okay, and this is your this gap. Okay, you go down, this is your Fermi level Fn. Again now you're creating the difference of Fermi level. First it was like this, now opposite means you're not like this. Okay, now here you have again majority charge carriers electrons. ये सब जो मैं बता रहा हूँ ये सब इंटरव्यू में पूछते हैं, ये सब जो आप इंटरव्यू में जाओगे तो ये सब ऐसे बना के बताना पड़ेगा. Okay, so this is electrons. Okay, and here you have a minority electrons, here you have a minority electrons, but you have a here positively charged holes. Okay, there is a majority, but now since the barrier is there, they cannot move, they will go and collide back, Okay, similarly this will go and collide back, this will go and collide back. Okay, but ये तो ऊपर है ना, ये तो this can come here ना, yes or no? This can come here and this can come here, because now the electric field here is the plus, is the minus, and here you have some minority electrons, minus minus. These minority electrons can be pulled by this one. Okay, so this movement is possible, this movement is possible, and this movement is possible, or the here to here is possible. It can combine with this one. Okay, so now this movement is possible, this movement is not possible, this movement is possible, and this movement is possible because of what? Because of this drift. Okay, and this current is in a opposite direction. Earlier current was flowing like this, now current is flowing there like this. Okay, so in reverse, when p-n junction is reverse bias, a reverse current flow, a reverse current flows, okay, due to minority charge carrier, due to drift of minority. Because as soon as electron comes here, this electric will catch this electron and then they will pass to the other section of this side of the section. Okay, so a reverse current flows due to the drift of minority charge carriers. Okay, and this current is in the negative direction, which I was showing, but this, because the number is very low, so reverse current value is low, very low, very current is in microampere, and the forward current is in the milliampere. Okay, forward current is the milliampere. That is the difference. Okay, so now finally, what is the story? In p-n junction, diode is basically p-n junction. It has a barrier, and you want to barrier it, you want to flow a current in the forward bias, you have to apply some voltage. Even reverse bias, you can apply some voltage, you can flow the current, but that current will be in microampere. Now let me draw the IV characteristics of p-n junction. So only itna story you require for your diode part. Okay, so now I will put the heading IV characteristics of p-n junction. IV characteristics of p-n junction. Okay, so when you apply, you have a p-n junction. Now I'm not drawing this this part. Okay, only I put p here, n here. Okay, so you have plus and you have minus. You're applying a voltage. Okay, polarity plus or minus. Okay, so when you're applying this one, because there is a built-in potential, current cannot flow without applying voltage. When you apply some, when this applied voltage become greater than the VBI, okay, built-in potential, and then current will start increasing exponentially as a function of voltage. So this is your I. So I is in milliampere, okay, and this is some volt, okay. But voltage value is not very high, because we some say 0.1 volt, 0.2, point, say 1 up to here is, say here up to here is 1 volt, say here this is 2 volt. So for, if your p-n junction is made of silicon, okay, so silicon p-n junction, for silicon p-n junction, this built-in potential value, built-in potential, okay, value which is written by V gamma is around 0.7 volt or 0.65, 0.6, or you take 0. V gamma. Built-in potential is 0.7 volt if your junction is made of silicon. Okay, for germanium p-n junction, of course impurity will be added, but the host material is germanium. Okay, for germanium p-n junction, this is also fourth group element. Okay, built-in potential V gamma is 0.3 volt. That values you have to remember. So if you want to flow a forward current in a PN junction, you have to at least you have to apply this much voltage. Okay, so if I plotting this for silicon, I have to apply 0.7 volt here, and after that current will increase exponentially. If it is germanium, I have to apply at least 0.3 volts. Okay, after that current can start. Okay, and if I go in reverse bias, this is a forward current, this is a forward current, which is exponentially depend on voltage, forward current. And there is a, if I go negative, there is a reverse current, which is value is very less. This is a reverse current, negative direction, okay, opposite direction. And this current is in microampere, microampere. This is called reverse saturation current, reverse saturation current, okay. And at particular voltage, say VR, this junction will break down, okay, break down because again it become conducting. Because all the board, if you apply so much voltage, what will happen? Because of impact ionization, all the sorry, bond will break, and suddenly there is a lot of junction, a lot of charge carriers are produced, which give high amount of current. But then junction is not giving these characteristics, that become like a resistor, okay, because everything is broken. Now there is no junction remain. So this becomes just like a ordinary resistor. Okay, so we have to avoid this breakdown voltage. This is a breakdown voltage. So we have to avoid this breakdown voltage. So whenever I say in the circuit I'm applying voltage in reverse bias, you have to assume that is less than the breakdown voltage. Okay, there's always less than the breakdown voltage. But whenever there is a reverse bias applied on the PN junction or diode, a current which is microampere will flow. I can take this current as a 0. So I will say whenever diode is reverse bias, or PN junction is reverse bias, it does not flow any current, because microampere current, that means no current actually. Okay, so you can behave like a junction can behave like an open circuit. Diode will behave like an open circuit. It will not allow any current. But practical calculations, circuit calculations, you can assume like this. Okay, and forward bias, it flows high amount of current. Okay, but after allowing, after applying, after when the voltage is greater than this one. Okay, so this is forward bias, this is the reverse bias, and PN junction can be replaced by diode symbol. Diode, this is the P part, this is the end plate. Okay, I can always replace. So for forward bias, I have to apply this one, plus minus. So whenever this is higher potential, this is a lower potential, this is forward bias, and then current will flow here, current will flow. And whenever it is the reverse bias, okay, reverse bias means this is your plus, this is your minus. Okay, so only reverse saturation current flow, IS will flow. Okay, IS is called reverse saturation current. IS is the reverse saturation current, and this forward current is represented by I forward. So a reverse saturation flows when you apply a reverse bias. Okay, तो ये point है. So basically क्या है कि this current is exponentially increasing. So while you are dealing a diode in a circuit, you can assume that drop in potential across the diode is always constant. If it is silicon, diode will be, the voltage drop across the diode will be 0.7. Always. If it is germanium diode, the voltage drop across will be 0.3 volts. Okay, like resistors, some you apply some voltage, some current is flowing, some voltage drop should be there. Okay, so here we'll assume that because the voltage variation is very small, here voltage variation is very small, so even though you are keep on increasing the voltage across the diode voltage will not increase, it will remain constant at 0.7. If the silicon, it remains 0.3, because in the circuit you are increasing the voltage, this voltage, there's some element current, some other elements are there, resistance are there, but because this variation is small, okay, because exponentially increasing current, so for practical purpose I can assume the voltage drop will be fixed for diodes. Similarly, when it is reverse bias, the current is constant, and if it is negligible current, So I can say my diode is not flowing any current, that is I can treat it as an open circuit. Okay, so let me now tell you how to how we can deal diode in the circuit, and before that let me just give you equation of diode. Okay, so this characteristics, this behavior of the diode can be modeled like this. Okay, so this is your forward current, this is your reverse current, and this is the exponential q v beta n k t. This is the applied voltage. Okay, -1. Okay, this is the, I am putting a applied voltage. So when applied voltage VA is positive, it is a forward bias, applied voltage is positive. Okay, then what will become this? And let me tell you what these things. This VA is applied voltage. Say this is applied voltage. This is applied voltage. Okay. Eta is diode constant. Okay. I forgot the name. What we called it? Extrinsic, some coefficient is there. Okay. So this is a diode constant. You say diode constant. Diode constant. Okay. For ideal diode, eta is 1. Okay. For germanium diode, if diode is made of germanium, that then you can take eta equal to 1. For silicon diode, until it don't say it is ideal, for silicon diode, in the exam it will say silicon diode, then you have to take 2. If say ideal, you take eta equal to 1, or if it's silicon, you take eta equals to 2. Okay, K is a Boltzmann constant, you know, K is a Boltzmann constant. K is Boltzmann constant. What is the value for this one? 1.38 to 10 raised to power minus 23 joule per Kelvin. Okay, T is a temperature in Kelvin. T is a temperature in Kelvin. T is a temperature in Kelvin, degree Kelvin. IS, I told you this is the forward current. Or you just write a not a forward, just write a current. Okay, we'll see what when is the forward. This is current, and this is a reverse saturation current. This is a reverse saturation current. Okay, so this is called Shockley equation, ideal diode equation. Okay, this is called diode equation. Diode equation, or you call it Shockley equation. Shockley equation. Shockley equation of diode. Okay, so let me now explain this curve with this equation. ये लिख दिया तो बताओ.
Yes, sir.
Okay. Now this is your. So whenever we apply this forward bias, okay, I can write this current as I forward, IS exponential. I can write Q VF eta KT, and I can neglect this one because it's an exponential current. Okay, so this will be my current, exponential current after this one. Okay, if V applied is reverse bias minus VR. Okay, then what become I reverse become IS exponential minus QVA upon eta KT minus 1. Now this VA is very high, exponential 4, 5, 6 volt. Okay, here the scale and here the scale is different. Whenever you draw IV characteristics of diode in your laboratory, you always take a scale. Here scale is different, here is scale is different. Okay, this is compensated scale. Compensated scale. These are different. Here is you always take a different scale because the voltage is less. Here you take high scale is higher. Here 1 centimeter maybe 1 volt. Are you getting? Okay, 1 centimeter 1 volt, 2 volt, 3 volt, 5 volt, 1 centimeter maybe 2 volt. Here it may be different. Okay, because here your scale is different. You require less voltage. Here you require higher voltage. Okay, so 3 centimeter here 6 volt. Here 3 centimeter maybe 1.5 volt. So scale is always different. So this voltage is very high. So whenever this voltage is high, this part becomes 0. and the reverse saturation current IR will be just simply minus IS. That is a constant current will flow. Just a constant current will flow for reverse bias. That you have to remember. And this is the forward current. Okay.
Sir,
Just tell me.
sir, IR is reverse current only, no, sir?
Yes, reverse current. IR is equal
IR is reverse saturation current.
IR is equal to minus IS. And IS is what? Reverse saturation current. Means direction is, if you are applying voltage like this, so current will flow like this. If you are applying voltage like this, current will flow like this, na? So if I'm saying this is the positive current, when applying plus here diode to diode, okay, current is flowing like this. When I'm applying plus here minus here, current is flowing like this. Okay, so I at least one current I have to take different, na? Minus, na? Opposite
Okay, sir.
opposite direction. So that way is that these things. Okay, so we'll talk this one later. Okay, so this is our p-n junction part finished. Okay, now we have to, and now I know the IV characteristics also. So let me now say how diode can be treated in the circuit. Give me a 5-minute break for just drinking water. I'll come back. Okay, so I'm not back. So can I continue?
Yes, sir.
So in order to deal diode, okay, in a circuit, diode in a circuit, diode in a circuit. Okay, so there are, this is not resistance. Okay, this is a non-linear device because I is not proportional to V. When you're applying V, current is changing exponentially. Sometime interview they'll ask like this. Okay, you have to remember this is not a. You should remember the IV characteristics of this diode. Okay, this is exponential dependence. So whenever you want to deal diode in a circuit, there are two models by which you can deal the diode in a circuit. One is called ideal diode model. Ideal diode model. Okay, another is called fixed voltage model. Okay, fixed voltage model, fixed voltage model. Yeah, voltage model. Okay, and the third is called piecewise linear model. Piecewise linear model. Okay, so this model says the resistance of the diode is 0. Okay, resistance can be 0 when it is a short circuit. Okay, so this model says that diode model because diodes behave like a short circuit. You can replace diode by a short circuit. Why? Because this model says the resistance of diode is negligible. So negligible means there is a no drop. There is no drop. That means you can flow only current. It can pass current according to the circuit or how much current is flowing. Without the drop of the voltage, current will flow. Okay, and this we'll discuss now in detail. And this model says no, diode has some voltage drop. Okay, so a fixed voltage drop is written here. So diode in this model can be replaced by a battery of V gamma, either 0.7 or 0.3. Okay, and other model says piecewise linear model. This says diode has some resistance also. Okay, this model says resistance, no voltage drop. This says no resistance, but voltage is there. This says voltage is there, resistance is there. Okay, so this model says you can replace diode by a battery of V gamma plus a forward bias resistance. Okay, in forward bias, reverse bias, all models are same. Reverse bias, all model says diode is open. Okay, so diode is reverse bias diode whenever it is reverse bias. This is forward bias for forward bias. It's for forward bias. Forward bias. For reverse bias, you can treat diode as a open circuit. Okay, it's very easy. Just within a couple of minutes, we'll understand what is the meaning of this one. Okay. So let me first start with a ideal diode model. So ideal diode model says there is a no drop across the voltage. So ideal diode model says test a current ID will flow through the diode. So when you're applying forward bias, okay, for forward bias, this is a forward bias. You're applying a little bit forward bias, that is positive terminal is slightly higher voltage greater than the negative terminal. Whenever you apply positive voltage, so drop across the diode will be zero and a current will flow through the diode. And when you're applying a reverse current, is dark part, okay, then I0 reverse part. If you're applying reverse voltage, forward voltage, drop zero, but current can flow, that is, it can behave like a short circuit. You have a diode, this one. If it is a slightly positive, it is slightly compared to this one, okay, that is called forward bias. And in the circuit, this forward bias can be replaced by a short circuit. Okay, but if across the diode, this part is negative, this part is positive, okay, this part has higher voltage compared to this one, this is called reverse bias. This is called reverse bias. In that case, diode will behave like an open circuit. That you have to remember. Okay, so this is the ideal diode IV characteristics. Ideal diode IV characteristics. Okay, so let us discuss in detail. So first we'll assume ideal diode model and we'll solve all the problems assuming diode is ideal. It will be given the question that diode is ideal, okay, or silicon. It will not tell just silicon germanium, it will say simply diode is ideal. Okay, so you should assume diode is either short circuit or diode is open circuit. Okay, now you have to identify in the circuit whether diode is getting forward bias or reverse bias. For example, let me give you some diode. This part is grounded. Here I'm applying 1 volt. The diode is forward bias or reverse bias?
Forward biased.
So this is 0, this is 1. Positive plate is more, negative plate is less. So this is forward bias. Forward bias. So that this diode will be replaced by a short circuit in the question. Of course, some resistance will be there. Okay, some resistance will be there. Okay, let me say let me put a resistance also here. Resistance R. So if this is the if no current is flowing, this part is 0. Okay. So when this is a forward bias, then only current can flow. If there is a no current in the beginning, this point, and this point are same. Okay. So this is higher potential. So this is forward bias. Okay. Because whether it is a forward bias or reverse bias, how can you assume? You just make it open circuit. Okay. Now say, what is the potential difference between this point and this point? Tell me. So this is at 1 volt, and this is at 0 volt. So there is a positive voltage difference. Yes or no?
Yes,
Understand?
sir.
So when you want to find whether a diode is a positive forward bias or reverse bias, just plug the diode from the circuit, and at the terminal you find the voltage. So here no current is flowing. So here this 0 is 0. This is a 1 volt. So this is a forward bias. So whenever you say forward bias, okay, so you identify this is a forward bias. This is a forward bias. Okay, forward bias. And what you do, and you can replace this by this circuit, and this is a 1 volt, and now you can find out what is current here, what is here. Okay, let me give you one more example. Say this is minus negative. Okay, here some resistance is there. Say this is plus 2 volt, and this is a minus 1 volt. Okay, yes, yeah, plus 1 volt. Here is a plus 1 volt. Tell me whether this is a forward bias or reverse bias. Tell me, is it forward bias or reverse?
Forward.
Okay, you will find a difference. Difference is positive, negative. So if I find a difference of this is 2 volt and this is a 1 volt, difference is positive. Okay, so this is a P terminal. P terminal is an N terminal. So Vp minus Vn is greater than 0, positive. That means diode is forward bias, and you can replace again this diode. No current is flowing at this point same. So this is so you can replace this diode 2 volt by a short circuit. Okay, and here is 1 volt, not 2 volt. Here 1 volt, and you can put a 1 volt here. Okay, so 1 volt by battery, something is there. Okay, and say so current will flow now in the circuit. So what I'm trying to say, whenever you want to find a diode is positive forward bias or reverse bias, you have to find this difference. Okay, let me give you one more question. You have a diode, a resistance is there, and this is minus 5 volt, and this is a plus 1 volt. Okay, tell me, it is a forward bias or reverse bias?
Reverse biased.
What is the value of VD? VP minus
Forward.
So forward bias.
forward bias. Okay, again you make it open. This is the P, this is N. The voltage drop across diode Vp minus Vn 1 minus 5 is plus 6 volt. Diode is forward bias. Okay, because forward bias means what? P with positive, N with negative. Either you make P more positive, or either you make N more negative. Both the meaning is same. That is a forward bias. Okay. Now let me give you one more last thing. Here plus 3 volt. Here plus 1 volt. Diode is forward bias or reverse bias?
Reverse biased.
This time it is a reverse bias, because VD, okay, Vp minus Vn is 1 minus 3 minus 2 volts. So it is reverse biased. So this circuit will be replaced by open circuit. This will be like this, +1 +3 volt. Okay, that is only you to do in the circuit. Okay, in solving the problems. So let us first solve the problem with ideal diode model. We'll do only 1 or 2 problems, okay? Then we'll continue tomorrow. So you have been given a circuit, say plus minus, this is a 10 volt, this is R, 1 kilo ohm. Okay. So here voltage drop is VD, okay? This R, okay? So voltage drop across this one I will call VR. Okay, this is R equal to 1 kilo ohm. So in the question it says find, and current in the circuit is flowing ID, is find ID, VD and VR. You have to find. Tell me how to find. How to find ID, VD and IR, VR.
तो डायोड सिलिकॉन का कि जर्मेनियम का?
आइडियल डायोड है, आइडियल डायोड. बात करनी नहीं है सिलिकॉन की, नहीं आइडियल डायोड है. सो फर्स्ट थिंग इज व्हाट, पहले सबसे पहले क्या पता करोगे? डायोड क्या है, फॉरवर्ड बायस और रिवर्स बायस. ओके, for that what you will do, you will open this diode from here. Now this diode is forward bias or reverse bias? बताओ भाई.
फॉरवर्ड बायस.
biased.
Forward
Forward.
bias. Because no current is flowing, that means this voltage will directly come here, 10 volt directly come here, and this is a minus, this 0 will directly come here. So diode is forward bias. Okay, so this diode here, this circuit can be replaced by what? This circuit can be replaced plus minus a resistance, and this is short circuit. This is a resistance, this is a 10 volt, and this is the VD, short circuit. Okay, current flowing ID, voltage flowing VR. Tell me what is the value of VD? VD कितना है circuit में?
0 volt.
0 volt. Very good. Okay, what is VR? What is VR? अरे भाई
10 volt.
10 volt. Voltage can be here or here. Here is 0, so all voltage is here. This is correct parallel to this one plus, and this is correct negative here. So VR is 10 volt. ID is what? The 1 kilo ohm. So 10 volt divided by
1 kilo.
1 kilo ohm. That is how much? 10 milliampere. 10 10 to the power minus 3. 10 milliampere. That much easy. It is even easier than the circuits what we are doing in the network analysis. Only you have to check whether it is a forward bias or reverse bias. Accordingly, you have to replace, and you have to solve the circuit. This is 10 milliampere. Okay. Let us do one more problem. Let us do same problem. I am putting this one here. Okay. Now tell me, diode is a forward bias or reverse bias?
Reverse.
रिवर्स बायस.
bias.
Diode is reverse bias. Very good. The diode is reverse biased. So you will replace Y plus minus plus 10 volt resistance. This will be replaced by open circuit. R, this is 1 kilo ohm. Okay. So this is your VD. Okay. Tell me what is the value of ID in the circuit? What is the value of ID in the circuit?
0.
0.
0.
Yes, circuit is open, so no current can flow. What is the value of VR? VR कितना होगा?
10.
तो VR कैसे लिखते हैं? I into R. तो R में करंट कितना है? ID into R. ID 0 है तो ये भी 0 नहीं होगा VR? फिर करंट ही नहीं है तो ड्रॉप क्यों होगा? आप सर्किट में करंट ही फ्लो नहीं कर रहा है तो यहाँ पे ड्रॉप क्यों आएगा? ड्रॉप आएगा नहीं, VR 0. VD कितना आएगा बताओ भाई? हाउ मच द वैल्यू ऑफ VD?
0.
सर्किट में देखो VD कितना 0 आ रहा है, कितना आ रहा है देखो, देख के ऐसे देख के बोलते हैं ना.
VD इनफाइनाइट.
इनफाइनाइट कहाँ से आ जाएगा?
-10 वोल्ट.
ये माइनस दिख रहेगा तुमको, यहाँ से देखो अच्छे से देखो. ये पॉइंट कितना है? इस पॉइंट का पोटेंशियल कितना है? इस पॉइंट का पोटेंशियल कितना है?
पॉजिटिव.
10 volt.
10 वोल्ट ही तो है भी. यहाँ पे ये करंट फ्लो नहीं कर रहा है तो ये जो 10 है ये ड्रॉप ही नहीं होगा, सीधा सीधा यहाँ आ जाएगा. और ये तो 0 है ही नेगेटिव, तो डिफरेंस कितना आ गया?
10 volt.
10 volt. So all the voltage will be applied across reverse bias. It will be applied across the battery. So VD is 10 volt. Okay. Now minus no, that student is correct, because we always measure VD by how we measure VD is VP minus VN. Okay, that is correct. Okay. So this is your VN. This is the VN. And this is your VP. VP. So this is at 10 volt plus 10 volt, and this is a 0 volt. Okay. So VD will be what? Your VP was 0 minus 10 volt. Okay. So that is minus 10 volt. Correct. Very good. That's the voltage. The VD is your minus 10 volt. Correct. Okay. So this way, last one more problem I'll do. Okay, and then we'll stop and we'll continue tomorrow. So the circuits are very easy. Just you have to find whether it is a forward bias or reverse bias. Okay. I am putting a 9 volt battery here, a resistance of 600 ohm, this 300 ohm. Okay, and then you have a diode here, and then you have a 100 ohm resistance here. Okay, now you have to find whether this diode is forward bias or reverse bias. Okay, so कैसे पता करोगे is forward bias or reverse bias? How can you find? Tell me. So obviously some 9 volt is coming here. Okay, some drop will there. Here some at least some voltage will come in the circuit. This is 9 volt will be divided here and here. Yes or no? So here what may some positive voltage will come. This part is connected to 0, but you should not never do this one. If you do like this, also answer will come correctly. But there's a probability of getting wrong. Sometimes mistake is more if you do like this. Okay, the best method I told you, whenever you want to find where diode is a forward bias or reverse bias, you just make it open. Okay, now you make it open. You see no current can go here. This 9 volt will be divided here and here. Some positive voltage will come here. Here no current is flowing. No current is flowing. So this is 0. So this is diode is forward bias. Directly you can say yes or no.
Yes, sir.
Here some voltage there. This 9 will divide between 600 and 300. So this will be 6 volt and this will be here will be 3 volts. Okay, and even you can do much better way, because this is open now. So remaining circuit you take a Thevenin circuit. Now here it is still correct. You find this is a positive volt and there is no current flowing. This is 0 volt. This is short circuit. You can do you can say you can find the ID here. Okay. Here diode is I removed, but diode is there. Okay, behave a short circuit. But what I'll do, the question, what is diode? Question is diode is idle diode, idle diode, and you have to find ID. Here you have a diode, and you have to find how much current is flowing here. Okay, so what I'll do, I'll first make it open. Okay, and now I'll find the Thevenin equivalent across this load. This is my load. Find the Thevenin equivalent. Tell me what will come Thevenin equivalent voltage. So Thevenin voltage, Thevenin equivalent voltage is what? Open circuit voltage. So V open here. How much will come?
3 volts.
3 volts. Same thing. 3 volts come. And R Thevenin. So here no current flowing here. So V open will be simply 9 divided by 900 into 300. So that is 1, that is 3 volt. And what is R Thevenin? Tell me across this resistance. Tell me what is R Thevenin? What is R Thevenin? So R Thevenin, you have to make this is a short circuit.
300.
So this 6 and 3 are in parallel, and whatever come in the series. So this will be 100 plus 600 into 300 upon 900. So this is 3, this is 3, this is 200. So become 300 ohm. Okay. So this circuit I can replace by a voltage source 3 volt and a R Thevenin of 300 ohm. And here you have a open voltage, you have a diode, you again, you keep diode again, put it diode again. Okay. Now you have to find the ID in the circuit, because the diode is looking that if you open this one directly, it is forward bias. You can solve like this. This is 300 ohm. This will be behaved by short circuit plus 3. Here voltage drop is VD 0 volt. Okay. This is 300 ohm. ID you want to find all the voltage getting drop here. So ID will be what? 3 volt divided by 300 ohm. That is 1 upon 100 ampere. Okay, that is how much? 10 raised to power minus 2 ampere. If I divide, that is 10 milliampere.
10 BPA.
10 milliampere current is there. Okay. And same circuit you can solve here also. If you put here short circuit, because you know this is a forward bias, so you can image directly, but you don't need to do this Thevenin circuit. But always it is helpful in complicated circuits. Just remove the diode, that become load. Remaining part you make a Thevenin equivalent and solve the circuit. Here also you do the same, current will come. Let us check. So suppose here 9 volt battery is there. I'm not replacing by this one. Okay, now I want to find how much current is coming here. So first I will find total current I. Total current I will be what? 9 divided by, these are parallel, and this is 6. Okay, so total resistance is 600 plus 300 and 100 are parallel. That is 400. Okay, cancel. This is 1. This is how much? 75. Okay, so this is 9 upon 675. If you use 3, कितना हो जाएगा?
225.
हाँ।
3 upon 225 हो जाएगा.
3 upon
3 upon 225. 225.
225. 3
5.
upon 225 ampere. This total current is coming here, or this current will divide here and here and here. Say this is ID, this is I1. Okay, you want ID. So total current 3 upon 225. Okay, 225,
Into 300.
and then
10 milliamps.
300 upon 400.
300 upon 400.
400.
Okay, so how much will come? Tell me again.
1 by 100. 1 by 100.
1, ये कैसे कटेगा? कैसे लिखा मैंने? 300. हाँ, कैसे कटेगा 100? बताओ. 225, ये कितना हो गया?
325 से हो जाएगा ना.
हाँ?
25 से क्या कहते हैं कट जाएगा ना. 225 और 300. Then we can simplify.
ये कट जाएगा? कैसे कटेगा? कटेगा?
9 times 25 से.
So 7 time ये 7 time and 5 time 75. Okay, and this 3 how much? 2 times, okay, 2 times 6 and 1 5 times. So 1 by 100. Again,
Yes, sir.
10 milliampere. Same is coming. So either you apply Thevenin equivalent or not. But I suggest you always apply Thevenin equivalent. Now possible हो, that will tell you clearly. This is simple circuit, so you know only this is forward bias. But there's a more than one sources, then you have to first judge whether it is a forward bias and reverse bias. Okay, then only we can decide what is happening. Okay, so we'll do many problems. So I is idle diode, and we solve a lot of problems so that you get practice. Okay, so I'll stop here.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.